goal of this lecture is I will say some method to verify a matrix be positive definite or negative definite or indefinite. Actually, today's goal of this lecture is this. At first, I will say some basic concept. Quadratic form. We all of us know quadratic form is look like x transpose ax. Obviously, Q be a mapping from Rn cross Rn to R. And consider Q of xy equal to 2x square plus 3xy plus y square. We can write this as x transpose ax, where x is the vector xy. That means, notice here we can write this quadratic form as x, the vector xy 2 3 0 1 xy. Here the matrix A is this. And notice here this means actually this quadratic form. Also, we can write this quadratic form in another way of matrix. We can write this as here 2 2 1 1, and this is also same as 2x square plus 3xy plus y square. That means I have got one idea. Any quadratic form can be represented as this type of matrix representation, but this type of matrix may be different. But when there exists unique matrix representation, then I will get any quadratic form as a same matrix representation. Okay? Oh well. We can write this quadratic form as a unique representation x transpose ax when A is a symmetric matrix. How this matrix would be? Notice this is equal to, we can write this 3xy in 2 divided part. That means here we can write 3 over 2xy plus 3 over 2xy plus y square. Then the matrix would be 2, here 3 over 2, here 3 over 2 and here 1. Then the matrix representation would be symmetric. And notice this matrix representation is unique matrix representation. That means from a quadratic form we can write this type of matrix representation is unique way when the matrix A is symmetric matrix. I hope my all viewers have understood this concept easily. Okay? Oh well. All of us know a quadratic form is positive when the quadratic form x transpose ax strictly greater than 0 for all non-zero x and q0 equal to 0 for x equal to 0. And the quadratic form is positive semi-definite if x transpose ax greater than equal to 0. This is true for all non-zero x. That means a symmetric matrix A and quadratic form x transpose ax are positive definite when x transpose ax strictly greater than 0. This is true for all non-zero x. Negative definite when x transpose ax strictly less than 0. This is true for all non-zero x. Positive semi-definite if x transpose ax greater than equal to 0. This is true for all x. When this is greater than equal to 0, this is true for all x, then this is the positive all non-zero x. And negative semi-definite, similarly, when x transpose ax is less than equal to 0, this is true for all x. And indefinite, when x transpose ax both positive and negative value. This is the idea of positive definite, negative definite, indefinite. We all have positive semi-definite, negative semi-definite. We all of us know this concept. In my previous video, I have discussed this concept elaborately. Also, I have discussed some example also. This is true when the vector space is real number. But when the vector space is complex number, in complex number, if we consider the bilinear from F from Cn cross Cn to complex number, then A is Hermitian if A conjugate transpose equal to A. That means given A belongs to M and C, we say that A is positive definite if V conjugate transpose AV strictly greater than 0, and this is true for all non-zero vector in CL. That means this is actually the definition of positive definite when the field is complex number. Here V conjugate transpose AV strictly greater than 0. And the geometry of positive definite actually, this means inner product V with V, who is defined as V conjugate transpose AV. And we all of us know inner product means actually this is the angle. So in inner product, angle defined as cos theta equal to V dotted with AV divided by norm V times norm of AV. Here the inner product is defined as V conjugate transpose AV, and since for positive definite for non-zero vector V, we have to prove this V conjugate transpose AV is strictly greater than 0. That means we have to prove this value strictly greater than 0. And we all of us know when theta lies between minus pi over 2 to pi over 2, then always cos theta would be strictly greater than 0. That means if we consider arbitrary vector V, then after transforming with A, then this can be, this may be the AV. Actually this vector lie minus pi by 2 plus pi by 2. Have you understood this geometry? Actual geometry of positive definite is, this is the vector V. If we hit this vector with the matrix A, then the direction of the vector always would be same. Then this is the positive definite. And when the direction of the vector after hitting the matrix A would be changed, then this would be the negative definite. This is actually the geometry of positive definite and negative definite. Now as for example, consider this matrix and prove that its matrix is positive definite. For this, take one vector in C2 where x not equal to 0, then inner product Ax with x, this would be x bar transpose Ax, and we have to prove this is greater than 0 for all x. Then here the given matrix is this. Here x1 bar, x2 bar, here x bar transpose means x1 bar, x2 bar, and here x1, x2. Then this is equal to 2x1, x1 bar plus I x1 bar, x2 minus I x1 times x2 bar plus 2x2, x2 bar. Okay. And from this expression, we can write this as x1 times x1 bar plus x1 plus I x2 times x1 plus I x2 bar plus x2 times x2 bar, and x1 times x1 bar is nothing but absolute value of x1 whole square, and this is actually absolute value of x plus I x1 plus I x2 whole square plus absolute value of x2 square, where x1 x2 not equal to 0. Then obviously this absolute value always greater than 0 for all x. That means I have got inner product Ax comma x is strictly greater than 0 for all x. Have you understood? Okay. Now I will see some condition which are equivalent in positive definite matrix. When positive definite matrix, when a quadratic form is positive definite, then these 5 conditions are all equivalent condition. All eigenvalue are positive. All submatrices have positive determinant. All pivot greater than 0. And next condition, if the given matrix defined as A transpose A then always this type of matrix be positive definite. When A has independent column, that means A has full rank, then in positive definite, these conditions are all equivalent condition. Okay. Now I will prove why in positive definite matrix all eigenvalue are positive. 1 implies always true. Positive definite always imply all eigenvalue are positive. Given x transpose Ax strictly greater than 0 because the quadratic form is positive definite. Here we have to prove if positive definite, then all eigenvalue are positive. Here Ax equal to lambda x. Now multiply this equation by x transpose. Then x transpose Ax equal to lambda x transpose x. Okay. And this is means lambda norm of x whole square. And since given x transpose Ax strictly greater than 0, that means this obviously strictly greater than 0 also. Since these terms greater than 0, that means lambda greater than 0. That means when positive definite, then all eigenvalue are all positive. Have you understood this concept? Okay. We all of us know determinant means product of the eigenvalue. So, since all eigenvalue greater than 0, so obviously product of the eigenvalue always would be greater than 0. That means determinant would be greater than 0. So, all submatrices have positive determinant and all pivot here greater than 0. And since in positive definite matrix determinant greater than 0, so that implies the matrix A always would be invertible. That means positive definite means the matrix always would imply this is invertible matrix because determinant is non-zero. Okay. And only positive definite projection matrix is A equal to identity matrix. Because we all of us know projection matrix means this is the idempotent matrix and the eigenvalue of projection matrix is either 0 or 1. But here 0. Means the matrix is positive definite. That means eigenvalue 0 cannot possible. That means only eigenvalue is 1. And since in the projection matrix only eigenvalue is 1, that means obviously the matrix is identity matrix. Okay? OL. Consider S equal to A transpose A. Now, this type of matrix always would be positive definite because quadratic from x transpose A transpose Ax, which is equal to obviously Ax transpose times Ax, and this is equal to norm of Ax whole square. Okay. That means since this is norm, so this is obviously greater than equal to 0. When greater than 0, then that implies obviously A transpose A is positive definite. Okay. And when equal to 0, then that implies positive semi-definite. And in the condition 5 given A transpose A is positive definite when A has independent column. When the matrix A has independent column. Because when A has independent column, then obviously Ax not equal to 0 because A has independent column. That means obviously the matrix A is invertible. Okay? And Ax not equal to 0. That means obviously the vector x not equal to 0. I hope my all viewers have understood this condition. That means a real symmetric matrix S is positive semi-definite if S can be factored. S equal to A transpose A. Okay? And S is positive definite if the matrix A is non-singular. Have you understood this concept? Okay. These 5 condition is if and only condition. When a matrix be positive definite, then these 5 condition would be all applicable. Notice this type of matrix. Here negative in 1 position. So this is not positive definite. Also consider this 2 cross 2 submatrix. Here negative determinant. Trace is negative because we all of us know sum of eigenvalue is negative. So obviously eigenvalue would be negative. Also this matrix is non-square matrix. So a square matrix A is negative definite if it is symmetric and x transpose Ax less than 0. This is true for all x non-zero x, and the equivalent condition is A has negative eigenvalues. The determinant of the matrix A principal submatrices are negative. A has negative pivot. This is the equivalent condition of negative definite matrix. That means when a matrix be negative semi-definite, then there exists at least one eigenvalue which is 0 and other eigenvalue would be negative. Okay? Then the matrix would be negative semi-definite. Now I will say another method to find a matrix be positive definite or not. Sometimes to evaluate the eigenvalue of matrix, this is very difficult way. So this criteria means Sylvester's criteria would be the faster way to evaluate a matrix be positive definite or not. Sylvester's criteria is consider a symmetric matrix A equal to A transpose. Then A is positive definite if and only if determinant of the top left K cross K block of the matrix A is strictly positive for all 1 less than equal to K less than equal to N. This is the Sylvester's criteria. For example, consider this matrix. Here I will use the Sylvester's criteria. Notice determinant of 2. At first used determinant of 2 is greater than 0. Then use determinant of this submatrix 2 minus 1 2. This is 3. Then determinant of whole matrix would be 4. Since determinant of all submatrix be positive, so here by Sylvester's criteria we can tell the matrix A is positive definite. Have you understood this concept? I hope my all viewers have understood this concept easily. Faster way to define positive definite of matrix. This is the best way, Sylvester's criteria. I hope my all viewers have understood this concept. Now I will define this example. I have defined this example in my previous video by quadratic form, but today I will discuss this example by Sylvester's criteria. Notice, by this quadratic form, we can write the matrix as 0 plus half 0. And here A equal to 0 and determinant of the matrix is minus 1 by 4, which is less than 0. So, this is not positive definite. Second, x square minus xy plus y square. We can write this as A equal to 1 minus half 1. Here A equal to 1 and determinant of the matrix is 3 over 4, which is obviously greater than 0. So, this matrix is positive definite by Sylvester's criteria we can tell. And notice option 3. This quadratic from x square plus 2xi plus y square. The matrix A would be 1, 1, 1. Here A equal to 1 and determinant of the matrix is 0. So, since determinant equal to 0, that means this matrix is not positive definite by Sylvester's criteria we can tell. And by this quadratic form we can write the matrix as 1, 0, here half, here also half. So, A equal to 1 and determinant of the matrix equal to 0 minus 1 over 4. This is less than 0. So, option 4 also not right option since determinant of the matrix is negative. So, by Sylvester's criteria we can tell easily matrix is positive definite or not. Today I will stop here. In my next video, I will discuss some example which had come in different comparative exam. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.